Hello, 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 hello. It is 2:55 p.m. Eastern Standard Time, afternoon, Friday, end of the week, October 13th, year 2023. My name is Mark Kulak. Houstonic.live is the name of the channel. For those of you who have watched the program, you know the deal. You know the mission. You probably have some familiarity with me by now. This is part 9 of a reading. This is a series where we are reading an article from the written in Britain, part of the British Health Institutes. They have a information website called whatisbiotechnology.org. And in this series, we are, which was titled The Story of Cesar, Milstein, and Monoclonal Antibodies. We have one episode, which was just an addendum that we did 2 days ago. A bit of a breakout about a co-founder of Centocor who passed a bit young. I don't think there was any reason to believe there was foul play, but just highlighting someone that helps us with some connections on this particular topic. If you go to whatisbiotechnology.org, index, exhibitions, Milstein is where you can get the URL. Other than that, every section so far has episode of this reading has corresponded to one section. So 1, 2, 3, 4, 5, 6, 7, 8. The 8th section is the first clinical applications of monoclonal antibodies. A bit of a longer section, but this is part 9 because, hence, as I just said, we had one additional addendum. So hopefully we can finish this in an hour. That would be absolutely awesome. Happy Fridays, end of day's prophet. Good to have you here, my friend. Happy Fridays to you and to everyone else out there. Hope everyone is enjoying the fall. Finally, at least within the United States, it has been some interesting weather this year. It's always whatever. Don't even want to go down that particular that path. Let's just stick to the mission at hand. Okay, section 8, and this is the 9th episode again. Harnessing the value of monoclonal antibodies. First subsection: using monoclonal antibodies for clinical applications. And at this juncture here, we're just going to zoom down a little bit. And here we go. Early on, Cesar Milstein recognized that the hybridoma technology he and Kohler, that's Georges Kohler, had devised might have useful applications, but that he would have to demonstrate what it could do before it would be adopted. Temporarily, he had to drop his basic scientific investigation into antibody diversity. The key challenge he faced was proving the value of monoclonal antibodies over conventional polyclonal antibodies for different applications. This would not be straightforward and would require the help of others. One of Milstein's first collaborators in demonstrating the practical application of monoclonal antibodies was Claudio Coelho, Cuello, a fellow British-Argentinian neuroscientist, who was then attached to the MRC's Neurochemical Pharmacology Unit in Cambridge. Their collaboration continued even after Coelho moved to the departments of pharmacology and human anatomy at Oxford University in 1978. A probe for neuroscientific investigation. Cesar Milstein and Claudio Coelho started thinking about how they might work together soon after Kohler and Milstein published the August 7th, 1975 article in Nature titled Continuous Culture of Fused Cells Secreting Antibody. At the time, Claudio Coelho was wrestling with the difficulty of characterizing substance P, or SP, known from the 1930s to be involved in pain and neurotransmission. His objective in this research was to determine whether SP was a peptide transmitter and to map its pathway within the body so that he could unravel the relationship between SP and disease. When Claudio Coelho began his collaboration with Milstein, he and his team had already gone some way to characterize and visualize SP. Again, SP stands for substance P. Yet this work had been laborious and time-consuming, and their method was unreliable. The technique they were using for the research was immunohistochemistry, an immuno-based test, which by then was a commonplace procedure. The method exploits the binding mechanism between antibodies and specific receptors on the surface of cells to enable the analysis and identification of different cell types. In this context, antibodies are tagged with a label, such as a fluorescent dye, to serve as markers for locating receptors on the surface of a cell. This allows scientists to measure and track particular cells in biological samples, such as tissue or organs. The major advantage of the immuno-based test was that it could be done in conjunction with an electron microscope. However, the technique had a major drawback in the early 1970s. It was reliant on the use of antibodies sourced from animal serum. Known as polyclonal antibodies, such antibodies are difficult to work with. They are heterogeneous and vary from preparation to preparation, which means they require extensive purification before use. Not only are polyclonal antibodies hard to standardize, they have a limited shelf life. Such characteristics made it difficult for scientists in the early 1970s to reproduce their own results and compare them with those of other scientists running similar immuno-based tests. When Claudio Coelho and his team were using their immuno-based tests to characterize SP, substance P, let me restart this sentence. What Coelho and his team were using for their immuno-based tests to characterize SP or substance P were antibodies taken from guinea pig serum. There is no... How do people think of this stuff? Just taking random animals out from God's animal kingdom and... sorry. Narrator's gasp of frustration and over. This, however, posed certain challenges. First, the antibodies taken from such serum were limited in supply. Secondly, they often cross-reacted with other substances as they were not specific to substance P or SP. Also note, hello, Kim Traveler. You haven't finished yesterday's stream yet? That's totally cool. I will probably republish yesterday's stream in a cut-down version. I had a long intro there where I was setting some stuff up. There were a couple moments in the middle where I was trying to find content, specific content to answer questions in the show on the screen. I could probably cut it down by 10 to 15%, and I will probably repost it on the Live 2 channel, and that's what I will also put on the other channels. So you'll be watching the full-length version along with my little rant at the end in response to what about the stance on viruses. Getting back to business here. On chatting with Claudio Coelho in 1975, Cesar Milstein quickly realized that the technique for raising monoclonal antibodies presented a potential breakthrough in the difficulties Coelho was then facing. Crucially, it offered the possibility of generating unlimited standardized antibodies which specifically targeted SP or substance P. By helping Coelho create a monoclonal antibody specifically for SP, Milstein not only helped to aid Coelho in his work, but also to satisfy his wider agenda, which was to demonstrate the practical utility of monoclonal antibodies. And this is actually an interesting, well, I'll add a little spice to this one, okay? A little narrator, a little additional narration here. Note monoclonal antibodies is really also a suggestion of a monoclonal line of cells. It's, of course, there are, you're harnessing the antibodies, but the antibodies are made by the cells. And it's a continuous line of cells which do not change from generation to generation that yield that specific antibody, right? Because the cells don't change, presumably if you have standardized laboratory conditions, you now have predictability and repeatability with respect to tests. You can't do science if you don't have, well, maybe that's too broad of a stroke, but most scientific experiments require standardization and repeatability. You haven't really learned anything if you can't repeat the test. If you can't repeat the test, then you haven't really nailed anything down in particular, right? This is a lot easy. This is one thing to do with cells. It is, I suspect, another thing to do with what the cells secrete. I wonder, we can understand with the monoclonals, but you're not. When it comes to cloning other stuff, you can see that it could be trickier. The more complicated the thing that the cell lines are, how would you say, producing, yielding, expressing, the more complicated the structure, you could see how difficult it would be to ensure that you have a consistent generation of those increasingly complex structures. And what I'm really talking about is, of course, exosomes and virus particles. Virus particles are many proteins arranged to build a very large object. The size of an antibody is pretty as complicated and as remarkable as they are. Is relatively controlled in scope to the size of a much bigger object that holds a much larger and much more complicated payload. You've heard much discussion about the difficulty with repeating, cloning, isolating, and so on and so forth, viruses, and there's much to be said about that. Matter of fact, the only way they know how to isolate anything is to find something that actually winds up cloning in a great enough number. There's just no way to be able to go in with a pair of tweezers and select an individual virus out and then, put it on inspect it, break it down. You actually have, the only way you can really isolate is through cloning. Very different when it comes to the cells, though. Cells, anyways. Just there's a whole lot to consider there. So getting back to this, actually this little diagram here, what does this show? Fluorescent staining and tagging. So here they're actually using the fluorescent staining of an antibody. So they're adding a characteristic to an antibody, which then binds to a particular cell, and then they're using that to identify cells. This image illustrates the binding of a tagged monoclonal antibody with an antigen receptor on a cell surface, which is the mechanism exploited in immuno-based tests. On chatting with Cesar Coelho in 1975, Cesar Milstein quickly realized that the technique for raising monoclonal antibodies presented a potential breakthrough for the difficulties Coelho was then facing. Crucially, it offered the possibility of generating unlimited standardized antibodies, which specifically targeted SP, or substance P. By helping Coelho create a monoclonal antibody specifically for SP, Milstein not only hoped to aid Coelho in his work, but also to satisfy his wider agenda, which was to demonstrate the practical utility of monoclonal antibodies. When Milstein and Coelho started their experiment to develop a monoclonal antibody specific to SP, many were skeptical about the utility of monoclonal antibodies over polyclonal antibodies. By 1979, however, the two scientists had succeeded in generating a monoclonal antibody specific to SP, substance P, that provided a highly effective tool for characterizing the neurotransmitter peptide. Milstein and Coelho's collaboration on SP, substance P, represented the first of many applications of monoclonal antibodies in neuroscience. Within a short time, Coelho and Milstein, together with other colleagues, were using the hybridoma technology to develop monoclonal antibodies for the detection and mapping of other neural proteins, including serotonin and enkephalin. I'm not sure what enkephalin is. ENKEPHALIN, With their monoclonal antibodies, Milstein and Coelho had opened up a new world in neuroscientific dissection. This would help lay the foundation for better understanding of diseases like Alzheimer's and Parkinson's, providing the pathway to improving neuropharmacological drugs. A new tool for immuno-based diagnostic tests. If monoclonal antibodies could be generated to target specific neuropeptide transmitters, Milstein realized monoclonal antibodies raised against other targets could be used in a whole range of immuno-based tests. This, he believed, would help encourage the adoption of monoclonal antibodies into what had already become a routine procedure for diagnosis in the 1970s in fields such as parasitology, virology, and cancer. Monoclonal antibodies offered such immuno-based diagnostics as unlimited standardized reagent, which could be used in thousands of tests with the same reliability and reproducibility. In addition to extending the boundaries of neuroscientific investigation, Milstein and Coelho's efforts helped improve immuno-based tests overall. Significantly, their work inspired the revival of many techniques which had been neglected because sources of polyclonal antibodies were inadequate. One of Milstein's and Coelho's key contributions was to help cut down the number of procedural steps involved in the making of immuno-based tests. This they achieved by demonstrating the possibility of conjugating monoclonal antibodies with enzymes and radioisotopes to act as tags in the immuno-based tests. The next section is called bispecific antibodies. The power of immuno-based tests was further enhanced by Milstein and Coelho's development of bispecific antibodies. This combined two antibodies that recognized two different antigen epitopes that is the portion of the antigen that binds to the antibody. The specific antibody was advantageous because it provided a tool that bound two different antigens simultaneously. This enabled the development of a single-step assay system as it eliminated the need for a second antibody. In the case of immunohistochemistry, it also helped improve the sensitivity of the test, simplified staining procedures, and improved signal detection. This work was published in Milstein and Coelho's 1983 article titled Hybridomas and Their Use in Immunohistochemistry. The paper inspired the rapid development of various bispecific monoclonal antibodies against different targets. Within a short space of time, a wide number of researchers had become involved in raising bispecific monoclonal antibodies. Some idea of the upsurge in this field can be seen from the fact that between 1989 and 1997, 5 international conferences were convened to debate bispecifics, not only for diagnostics but also for therapeutics. By the year 2012, more than 40 different formats of bispecific monoclonal antibodies had been designed and produced in the laboratory for clinical investigation, and more were in the pipeline. Next section is called Another Patent Opportunity Missed. Oh no! Another patent opportunity missed. Ooh, this could be interesting. Of course it will be interesting. On October 6th of 1983, Milstein and Coelho's technique for producing bispecific antibodies was filed for patent protection by the British nanotechnology company called Celltech, Celltech. Although Milstein and Coelho had been the first to demonstrate the ability to make bispecific antibodies, to their great surprise, the patent application was later abandoned by Celltech and the MRC. The application was dropped on the grounds that a patent had already been filed by the University of Texas. Although this application had been filed on the basis of a theoretical proposition rather than a practical demonstration in legal terms, it implied that Milstein and Coelho had only put into practice an experiment predicted some time before. This undermined any possibility of success with the patent application. Celltech. Heard about that company recently. The abandonment of the patent for Milstein and Coelho's technique is particularly striking, given that today bispecific antibodies are growing in popularity for therapeutics. It could be argued that, yet again, an important patent opportunity was missed. Some researchers doubt, however, that any substantial revenue could have been earned from any bispecific monoclonal antibodies produced from hybrid hybridomas during the lifetime of such a patent. Next section is called the means for sorting and identifying cell subtypes. Soon after starting his work with Coelho, Milstein began another collaboration that would help demonstrate the utility of monoclonal antibodies in another field. His partner in this endeavor was Leonard Herzenberg, Herzenberg, an American from Stanford University Medical School who arrived in Milstein's laboratory in 1976 for a brief sabbatical. During his visit, Milstein and Herzenberg, it's Leonard Herzenberg, began working together on the development of monoclonal antibodies to improve the utility of a fluorescence-activated cell sorter, FACS. This was a machine that Herzenberg and some engineering colleagues had devised in the early 1970s to automate the separation of cells. It was designed to help characterize, isolate, and count different subsets of cells, notably white blood cells, that coexist in blood and various organs. And this is a picture here on the left. That's Leonard Herzenberg, and on the right, that's his wife, Leonore Herzenberg, who was also a fellow geneticist and immunologist. By the time Herzenberg arrived in Cambridge, his FACS, and again, that stands for the fluorescence-activated cell sorter, could sort 5,000 live functional cells per second. Wow. And it was being marketed by the medical device company Becton Dickinson. That's Becton and hyphen Dickinson. The FACS, however, still had some teething problems. One of the key challenges was that the FACS, and again, that's the fluorescence-activated cell sorter, like other immuno-based methods at the time, relied on polyclonal antibodies. These antibodies, conjugated with fluorescent tags, were integral to the sorting mechanism in the instrument. Such antibodies targeted receptors on cells to facilitate the picking up and sorting of such cells with the use of a laser-detecting fluorescence. The difficulty was that these antibodies were not standardized and were in limited supply. Moreover, they had a tendency to cross-react. Conjugating these antibodies with staining agents was also laborious and slow. On arriving in Milstein's laboratory, Herzenberg immediately grasped the utility of monoclonal antibodies for improving the performance of the fluorescence-activated cell sorter. To this end, he partnered with Milstein to develop monoclonal antibodies for use in the FACS machine. Much of the research was undertaken with the help of Herzenberg's wife, Lenoir, or could be, and Vernon Oy, that's last name O-I, who was a graduate student from Stanford University. By 1977, Milstein and the Stanford scientists had generated the first monoclonal antibodies in mice capable of use in the fluorescence-activated cell sorter. Designed to screen determinants on the cell surface of many cells on a large scale, these monoclonal antibodies helped improve the reliability of the fluorescence-activated cell sorter and boosted their popularity for many different purposes. I want to look up, I'm sure there would be a Wikipedia page for Leonard Herzenberg. I'm just curious what it would say. Let's see here. He passed in 2013, 81. Immunologist, geneticist, professor, born in New York City, California Institute. He was at the Pasteur Institute in France. Talks about the FACS, fluorescence-activated cell sorter. Talks about his sabbatical with Cesar Milstein. His daughter, Jana Herzen, is a singer-songwriter and the founder of Motima Music. Interesting. Which is a jazz and world music record label. Finally. It sounds a whole lot more pedestrian to me than everyone just being one geneticist, one generation after another. Today, FACS, that's fluorescence activated cell sorter, is a ubiquitous tool within the laboratory. In biological research, for example, the instrument is used to investigate cellular functions, measure metabolic processes in cells, and work out how viruses infect cells. On the medical front, it is used for routine clinical tests involving the counting of white blood cells as is needed in diseases like AIDS, and for the assessment of the efficacy of chemotherapeutic treatment for diseases like leukemia. I will say, how viruses infect cells. A virus cannot make a cell do anything that a cell is already capable of doing. I'm going to repeat that. A virus cannot make a cell do something that the cell isn't already designed to do or capable of doing. Does that make any sense? A virus cannot punch a hole into a cell and then make a cell create proteins and do other gnarly stuff if the cell does not already have the capability to welcome in, based upon their encoding, particles like exosomes, process their instructions inside, and express proteins and manufacture proteins that are described within the instructions. A virus cannot make a cell do anything that a cell is not already designed to do. A virus cannot make a cell do anything a cell is not already designed to do. A virus cannot make a cell do anything that a cell is not already designed to do. Period. End of story. What that means is that everything that is and could be considered a virus is working within and as a subset of exosomal communication. 100% of it. That's the only reason viruses can exist, if you want to call them viruses. I have big questions about the nature of pathogenic viruses overall, because I don't know why nature would evolve such a thing. But nonetheless, it is what it is. It's such an important concept to consider. It's sort of like the Unabomber, the mail bomber, took advantage of the mail system. The mail bomber took advantage of the fact that there's postal office trucks and mailboxes and sorting and planes to transit packages. The mail bomber did not walk up to someone's house, saw a hole in their wall, throw in a package that said, "Open me." They used an existing system. They could not make the mail system do something it didn't already do. They worked within that system. I know it's sound like a broken record here, like a bad broken record. But as we study this more, never to lose track of that. It's one of the most, and it will help unravel so many things which are so confusing and help you spot the baloney out there. Okay, let's get back to business. Hey, Laura. Paulie, good to see you, Paulie. RT3, good to see you, my friend. Yes, this is a long and somewhat technical article. Something to put on while perhaps, who knows, whatever it is you're doing. I imagine that the size of the audience that will be glued to their headphones during this article is a smaller percentage of the population. Matter of fact, I don't even fully understand all of it myself, and that's cool. The next section, exploring the unknown terrain of the surface of the cell. Ooh. Hello, Christy. In addition to helping to develop monoclonal antibodies to enhance the sorting and counting of different cell types, Milstein became immersed in another project that would open up a new understanding of the surface of the cell. I like where this is going. His work in this area was triggered by a chance conversation he had at a conference at Cold Spring Harbor. I really like where this is going. In June of 1976 with Alan Williams, an Australian immunochemist based at Oxford University. Prior to meeting Cesar Milstein, Williams had spent many years attempting to purify antigens and antibodies in order to develop a probe that would distinguish between white blood cells or lymphocytes and to work out their functions. Such efforts were also directed towards identifying the cell surface molecules involved in the mediation of lymphocyte function. This he saw as a means to unraveling the biochemistry behind immunological reactions. By the mid-1970s, Williams and his team made a number of advances. Specifically, they had purified an antigen known as THY1 that proved to be an effective tool for locating T lymphocytes in mice. They had also identified a leukocyte common antigen using antibodies taken from the serum of rabbits immunized against rat lymphocytes. Oh my goodness gracious. Overall, however, they found it difficult to secure antibodies with the right strength and specificity for the target. Williams believed the technique developed by Milstein and Kohler might resolve such problems. Soon after meeting in Cold Spring Harbor, Milstein and Williams set up a collaborative project. The first monoclonal antibodies they chose to produce targeted a rat's thymus. Their choice of the thymus was deliberate as it is known to play an instrumental role in the immune system. Notably, the thymus produces T lymphocytes or T cells, which identify and attack foreign substances. That's what T cells are. Milstein and his team took responsibility for the tissue culturing involved in the project, where Williams' team in Oxford oversaw the serological work. The work was logistically difficult because 85 miles separated Milstein's laboratory from that of Williams. Writing about that work at a later date, Cesar Milstein recalled, quote, "The basic protocol of the collaboration was as follows. We produced the cultures and clones and sent the supernatants by urgent mail. As soon as we got them, Alan proceeded to do the binding assays, and usually within 24 hours, he would phone, no faxes in those days, the results, and perhaps 100 assays per round, for us to proceed with clonal selection. Speed turned out to be essential. We discovered that the contaminating clones or chain loss mutant all too often conspired against us. Indeed, literally hundreds and hundreds of failed attempts taught us a lot about the technical problems involved and how to tackle them." Unquote. Within months of having immunized mice with cell membranes taken from a rat thymus, oh my goodness, the two groups of scientists in Cambridge and Oxford had succeeded in generating mouse-based antibodies to rat T cells. The experiment yielded 3 monoclonal antibodies for distinct subsets of T cells in rats. One of the most promising monoclonal antibodies was codenamed W3/25. This later turned out to be the rat equivalent of a human antigen labeled CD4, which in the mid-1980s was identified as the receptor for the AIDS virus. Ooh. No wonder. And they did that work at Cold Spring Harbor, eh? When Milstein and Williams began their collaboration, it could be argued that scientists had as much knowledge about the surface of immune cells as they did about the surface of the moon. What was most exciting about their experiments was that they had shown it was possible to produce monoclonal antibodies to unknown cell surface antigens, and that such antibodies could be deployed to investigate and understand the function of such antigens on cell surfaces. Results from the Cambridge-Oxford collaboration were published in the Williams, Galfrey, and Milstein article, 1977, titled analysis of cell surfaces by xenogenic myeloma hybrid antibodies, differentiation antigens of rat lymphocytes. In this article, the scientists suggested that monoclonal antibodies might be developed in the future, not only for investigating immune cells, but, quote, for the analysis of cell surface molecules of any sort, unquote. Having generated monoclonal antibodies to rat T cells, Milstein began to investigate whether the process could be replicated for making such antibodies to antigens found on human cell surfaces. His partner for this work was Andrew McMichael, an immunologist based in Oxford who had an interest in human T-cell immune responses to viruses. Started in the spring of 1977, Milstein and McMichael's project was an extension of the research undertaken by Milstein with Williams. What Milstein and McMichael were interested in developing was a monoclonal antibody against human T cells. This, they believed, could help further knowledge of the immune response in human health and disease. McMichael and his team in Oxford were given the task of immunizing mice with human thymocytes, which are precursors to T cells that develop in the thymus, to generate antibodies against human leukocytes. The antibodies were then sent through the post for fusion with myeloma cells in Milstein's laboratory. Once fused, the cells were then returned by post, by mail, to McMichael's laboratory in Oxford, where they were analyzed. The work was not easy. Initially, the scientists battled to perfect a good fusion with the cells. Having finally achieved a good fusion, the project nearly collapsed when the cellular culture became contaminated with fungus. By chance, the team had earlier stored some cells in the freezer. These cells helped rescue the project. By late 1978, Milstein and McMichael's team had produced a monoclonal antibody that was highly specific to human thymocytes. This represented the first discovery of a human leukocyte differentiation antigen using hybridoma technology. Despite their achievement, Milstein and McMichael initially struggled to find a journal that would publish their findings. Notably, editors of the Journal of Experimental Medicine rejected their paper without seeking referees' comments. This they did on the grounds such work was of, quote, little scientific interest, unquote. Overall, the editors believed the paper did not describe anything particularly different from what was then being done with polyclonal antibodies methods. In part, the editors, quote, attribute reflected a more general lack of appreciation of the significance of the differentiation antigens. It also stemmed the failure in early days to grasp what hybridoma technology could achieve, and from the fact that many scientists were still struggling to establish stable and viable monoclonal antibodies. Somewhere in there is a close quote. Let's see here. Means to purify interferon. This is interferon. What is interferon? Let's go to Wikipedia page. Interferon, or IFNs, are a group of signaling proteins made and released by host cells in response to the presence of several viruses. In a typical scenario, a virus-infected cell will release interferons, causing nearby cells to heighten their antiviral defenses. INFs belong to a large class of proteins known as cytokines, molecules used for communication between cells to trigger the protective defenses of the immune system that help eradicate pathogens. Interferons are named for their ability to interfere with viral replication by protecting cells from virus infections. However, virus-encoded genetic elements have the ability to antagonize the interferon response, contributing to viral pathogenesis and viral diseases. I don't know about that. But it again, who knows? I'm not saying if this is all true. I understand that this is what's generally understood to be the model. But if this were to be true, it would make sense. If one cell had just welcomed in and is processing the payload of something that it thought it should deal with, but in reality was a foreign virus, particle, a foreign exosome, etc., it may go, whoa, something ain't right here. My buddies, similar cells, might fall for the same trick. So I'm actually going to, it's almost like a shortcut to an antibody, right? I'm actually going to create an interferon, so I'm going to help the other cells not make the same mistake that I just made. That's how I read it, right? So an antibody flags a foreign particle, foreign protein, foreign exosome, whatever, and then later on it's going to be cleaned up by the T cells, the killer T cells, taken away. However, that's somewhat complicated, and there may not be enough time for all that to happen. So this is more of like a simplified emergency response to other cells. Interferons interfering. So there you go. A means to purify interferon. And I find this interesting because there was a lot of interferon research, I recall, in the 70s around the topic. I don't know if we can find the history here. Around the topic of HIV. I remember hepatitis C, hepatitis B. There was a lot of talk of interferons. What's his name? Fauci. I remember talked a lot about these. The history. Interferons were first described in 1957 by Alec Isaacs and Gene Linderman, NIH. Result of their studies of viral interference. 57. Chicken embryo. You know who that means. And then, for example, during research to produce more vaccine against smallpox, a couple of Japanese guys, Nagano and Kojima, University of Tokyo. Anyways, there's a lot written here. I do remember that it was hepatitis and cancer-causing viruses research that you saw a lot of this stuff pop up. RNA, TansLab, Cetus Corporation, interesting. So that's a whole topic in and of itself. Means to purify interferon. In addition to exploring the use of monoclonal antibodies for probing the surface of cells, from 1976, Milstein began to wonder about the potential to purify natural products. He began working on this with David Cesar, Secher, who had been one of Milstein's doctoral students and was now his postdoctoral researcher. Curious to establish their utility for purifying natural products, Milstein and Cesar established a collaboration with Derek Burke, Burke, a biologist at the University of Warwick who had a long-standing interest in interferon, a group of natural proteins released by an organism's cells in response to pathogens such as bacteria, viruses, and parasites. The objective of the partnership was to develop a monoclonal antibody that might be useful to purify human leukocyte interferon. Since the late 1950s, researchers had deployed several methods for purifying interferon, but most could not yield the several thousand-fold purification for turning interferon into a pure and clinically useful product. One of the most promising techniques for purification was immunoabsorbent chromatography. The method allowed for the isolation and selection of the protein based on the binding properties between antibodies and antigens. However, the technique had a downside. It depended on the use of conventional polyclonal antibodies again. What made matters worse was the fact that scientists only had access to impure interferon. Most antibodies available were therefore made by immunizing animals with impure interferon. This meant that most antibodies available for the immunoabsorbent chromatography targeted contaminants in interferon preparations rather than the interferon itself. Encouraged by Milstein from the sidelines, Cesar and Burke next launched a project to produce a monoclonal antibody that could improve the immunoabsorbent chromatographic method for the purification of interferon. The work was painstaking and there were many false starts. Just before Christmas in 1979, Cesar and Burke were so disillusioned with their progress, they considered abandoning their research altogether. By March of 1980, however, they had created a system that yielded interferon that was about 100 times purer than anything managed before. Patented, Cesar and Burke's methods for purifying interferon was just one of many stepping stones on the way to the commercialization of different genetically engineered versions of interferon as a drug in the mid-1990s. It would be approved for marketing as a drug to control multiple sclerosis and as a treatment for cancer, as well as various infectious diseases, including hepatitis B and C. I think this is the last subsection here, a reagent for blood typing. As early as 1975, Milstein attempted with Kohler to make monoclonal antibodies for typing the rhesus blood group. They realized this could be helpful for blood typing, a technique that was important for ensuring safe blood transfusions. Little progress, however, was made. More success was to be had in generating a monoclonal antibody against other groups of blood cells known as type A. This emerged by chance out of the work Milstein did with Williams to generate monoclonal antibodies for differentiating antigens on the surface of immune cells found in rats. Milstein quickly grasped the potential monoclonal antibodies might hold for blood typing. At this time, all blood grouping tests were performed using conventional polyclonal antibodies drawn from antiserum. These antibodies acted as markers that would bind and clump specific determinants of the red blood cells. This helped determine the blood group classification. Up to the late 1970s, the bulk of antiserum used in blood typing was sourced from human volunteers. This supply, however, was limited. Moreover, the little that was available was under severe strain. In part, this reflected an upsurge in blood typing to meet the increasing frequency of major surgery and the fact that human blood serum was also critical for other medical purposes. The shortage was not helped by the fact that no two human sera are alike, and sufficient volumes of antiserum are difficult to secure with adequate antibody potency for giving reliable results. Excuse me. Wow, that's a powerful sentence. The shortage was not helped by the fact that no two human sera are alike. You mean there's that much difference? There's that much difference in antibodies? Are you trying to tell us that we're not just plug and play? Are they actually trying to tell us that there's no standardization? The more specific we get, the more we realize that there is actually a galactic level of diversity. For Milstein, monoclonal antibodies provided an important tool for standardizing blood group typing. To this end, he collaborated with Douglas Voak, V-O-A-K, a pathologist based in the Regional Transfusion and Immunohematology Center, which was located in Addenbrooke's Hospital, just over the road from his laboratory. Initially, the monoclonal reagent they created had some problems, but within a short time, they had produced one that showed itself an experimentally effective tool for typing blood group A. Soon after Milstein and Vogt started their collaboration, they were approached by Stephen Sachs, S-A-K-S, a medical graduate who had joined the Laboratory of Molecular Biology, the LMB, in 1978 to work as a doctoral student under Edwin Lennox, an American immunologist and founding member of the Salk Institute, who had arrived in Cambridge in 1974. Sachs was curious to understand a strange phenomenon he had observed among some monoclonal antibodies that had been generated against different cancer tumors. These had been made as a tool to investigate the factors involved in the stimulation of the immune response against a tumor. When placed together with a mixture of cancer cells on a small plastic plate, the cells showed an unusual clumping and a disc-like formation. Surprisingly, he found that in addition to targeting tumor cells, the monoclonal antibodies appeared to target other cells. With the help of Vogt and Milstein, Sachs discovered that he had inadvertently identified a monoclonal antibody that bound powerfully to antigens found on the surface of the human blood group type A. With Milstein's encouragement, we're almost done here, guys. With Milstein's encouragement, Sachs set about developing a monoclonal antibody reagents, together with Lennox and Vogt, for routine typing work. By 1982, the team had developed a number of different monoclonal antibodies suitable for routine use in ABO blood typing and had evaluated these agents against thousands of blood samples, both manually and through machines. These monoclonal antibodies were patented and commercialized by the newly created British biotechnology company Celltech, Celltech, which saw the reagents as fundamental to its growth. In 1982, the company's executives estimated that the world market for such products was worth $7.5 million in terms of hospital sales and $3 million in other sales. Not much, really not even big at that time. Within 7 years, over half the world's blood typing reagents would be based on monoclonal antibodies derived from those first developed in Cambridge and produced by Celltech. Just get that one curious. Is there a wiki page for Celltech? Just curious here. And then I think we're gonna go. I got to get back to my running around. Yeah, Celltech. Founded in 1980, defunct in 2004, Celltech was a leading British-based biotechnology group. It was on the London Stock Exchange, instrumental in changing the UK's system of technology transfers. Ooh, that's a heavy word. From research to business, and in creating biotechnology industry. Right around the same time that we had all the technology issues, technology transfer capabilities open up in the United States. To take all that technology at places like the University of Washington, for example, and turn it into tradable companies. So I'm sure there's a lot more to learn there. Anyways, guys, I'm glad we got that out. I think that was one of the... the next chapter is just the legacy part, so we're just about done wrapping this up here. I'll probably do a addendum on Kohler, Georges Kohler. If you go to Wikipedia, Kohler. He died as a consequence of a heart condition. That just sounds a little suspicious to me at age 48. Especially when you see here that he moonlighted as a taxi driver. He spent time with his children driving a small tractor on roads, enjoyed roller skating in the streets. I mean, who knows, sometimes healthy people have weak hearts, but I just wonder. Just ask questions. I'm sorry. And I should have, I didn't actually have the, I wanted to have this part up here. Georges Kohler. I apologize. I see that for some of this, I didn't have the part that I was reading on the screen. myself, just looking at the wrong screen, I guess, and I didn't realize I had made that mistake. So I apologize, everyone. But with that said, that's what bothers me in monoclonal antibodies. Kim says you're getting something standard that may, yeah. Look, it's a little weird, and they're made by effectively a cell line which should not exist in nature, right? These monoclonal, these line of cells, which are the same generation after generation, shouldn't exist. Look at all the crazy stuff they had to go through to make them. And then they're expressing antibodies, which are then harnessed and used for isolation, for experimentation, and for other research purposes. Now, I should say now for therapeutic purposes. Now, I don't know if the Milstein article gets into how companies like Regeneron, or I think it's Regeneron, or a few others, have used cell lines which involve human cells from abortions. There's several well-known cell lines used for the production of monoclonal antibodies from these monotonous lines of cells, which trace back to an aborted pregnancy, human pregnancy. In some cases, they date back to an abortion that was several decades ago, which is really bizarre. I don't understand what the moral implications of these are. That may differ person to person. That may differ religion to religion. Nor do I really understand the long-term consequences of these things. There is, however, I've seen a lot of anecdotal evidence of people who had certain illnesses and as part of their treatment responded favorably, not everyone, but responded favorably to monoclonal antibody treatments. Does it create additional long-term consequences? Excellent question. Unknown. Maybe one of the reasons why there's so much work being done to get away from monoclonal antibodies, encouraged by people like Sina Bavari, for example, is because it's known that there's something horrible about it. That's a possibility. But if there is, just say it then. Instead of saying it's about money. Just tell people. Anyways, the challenge is that in many cases they have been effective. And I do believe that the intellectual property and that it is an issue is huge. It's one of the main reasons. I also think that there's three things, right? One is the patenting and intellectual property issue. Two is that the more we talk about the intellectual property issue with monoclonal antibodies, it exposes a bigger biosurveillance and data collection agenda. And the third challenge here, I'm glad you guys are still hanging in there. The third big thing, how do you test monoclonal antibodies? Guess what? You have to see if the subject has health that improves. Just send me a yes in the chat that you heard this. The way you test monoclonal antibodies effectiveness, you see if the health improves. How do you test the effectiveness of mRNA or another vaccine? You merely need to test for the existence of the antibody, and that's it. Oh, this mRNA injection, transfection, we'll call it a vaccination, was effective because it created an antibody. It created something that we can measure. The effectiveness test of most vaccines has nothing to do with if someone has an improved health in response to it. All you need to do is measure a reaction. Think of the incredibly unfair competitive advantage that mRNA and other vaccines have compared to monoclonal antibodies. One, you actually have to make sure, because you can't measure the antibodies if you're just injecting people with the antibodies, because of course they already have them. You actually need to make sure that they get healthier. How frustrating. And that playing field is matched. You can't compare monoclonals against other vaccines. You can only compare them against interfering particles such as remdesivir. Remdesivir is tested the same way. Reduced hospital stays. What the heck is that all about? You can see. So those are 3 things we just listed there. And of course, the long-term responses. It is legitimate. And how you doing, Tyrone? Good to see you, my friend. Good. It is a very serious question. What are the long-term consequences on our physical health across generations, even spirituality, when using things which are just so incredibly unnatural? I know I often reference the crazy, it's not necessarily the best movie ever made, but the movie Death Becomes Her in the late 1980s, because it poses if something is done that can cause life extension or immortality, well, guess what? We're still subject to accidents. It's actually an impossible thing to attain. What happens if you can't die anymore? I don't know. What are the implications on some poor soul that did not get to live, perhaps legitimately because it was a mother versus child situation, right? I don't know the conditions of the terminated pregnancies which are used, but imagine if their cells are still alive. This is just bizarre. What's the impact on that soul? I don't know. I don't have those answers. Not to mention, can it cause even more health effects long term? I don't know. Anyways, I know I've definitely have sold a lot of the benefits of monoclonals, in particular the fact that there's been people who they've helped. And it's impacted. I mean, I've never used them, but some people really important to me have used them, and they got healthier. So to have a war on them just over money and patenting issues, to me is deeply frustrating. However, these ethical questions do need to be tackled at some point. I certainly don't have the answers, nor am I equipped to answer them. Ever answer them. Anyways, guys, thank you. Take care. That's been an hour and 2 minutes. Time to get back to my my running around endlessly and burning gasoline. So thank you, guys. Take care. I do appreciate all supporters making the channel possible as we are second month into our 5th year. We're going to keep doing daily stuff like this, even if it's just readings, and just keep marching on from there. I see it's having a positive effect. Be well, everyone. Take care. Love your neighbor.